Hey, Wheat North, Mr. Yergler here. We're going to talk about percent composition and empirical and molecular formulas. All right. By the end of the video, you should be able to calculate the percent composition. We're going to look at reducing formulas to empirical formulas and talk about the difference between empirical and molecular formulas, and then eventually calculate empirical and molecular formulas from a percent mass, okay, or percent composition. All right, so let's get started. Percent composition is pretty straightforward. Any percent is pretty straightforward. It's always the mass of the part over the mass of the whole. And so you just need to figure out what is the part that we're talking about and what is the whole that we're talking about, and then you can figure out percent. Just like you would do with your test, right? What part did you get right, and what was the total, what was the whole? That's how you calculate your percent grade, or your percent of the questions you got right. Okay. So for percent mass of hydrogen in phosphoric acid, we need to figure out what the mass of the hydrogen is, since that's what the question's asking. What's the mass percent of hydrogen in phosphoric acid? And then what's the mass of the whole thing, right? Which would be the molar mass. So our mass of our hydrogen is going to be 1. The molar mass of hydrogen is 1, and there's 3 of them, so it's 3 times 1. And then the mass of the whole molar mass is going to be the 3 hydrogens, the 1 phosphorus, and the 4 oxygens. Okay, take that times 100%, and 3% of the mass in phosphoric acid is from the hydrogen. So how would you find the percent mass of calcium in calcium hydroxide? You would need to know what's the mass of the calcium, and then what's the mass of the whole thing, the calcium hydroxide. So just like we did in the other one, the mass of the calcium, there's only 1 calcium in the formula, and so it's just 40. That's from the periodic table. And then the molar mass of the whole thing comes out to 54%. Let's say that a sample is tested in a lab type setting, and they figure out that 74.5% of the mass from the sample is from chlorine, and the whole molar mass, or the total mass, not the molar mass, the total mass is 190.2 grams. What would the mass of the magnesium be? Now again, you want to look and kind of make sure you understand what the question is asking. It's asking about the mass of the magnesium, but it gives you the percentage of the chlorine, right? So there's a couple different ways we can do this. We can take the mass, the percentage of the chlorine, and turn it into a decimal, essentially, right? 0.745. If 74% of the 190 is chlorine, then that means the mass of the chlorine is 141.7 grams. So then if 141.7 grams of the sample is chlorine, the rest of it has to be magnesium, right? And so you can just subtract the total from the mass of the chlorine to get the mass of the magnesium. You could do this in a different way. You could say that roughly 25%, what would it be, 24.5%? of the sample is magnesium, and then 0.245 times the total, and that would give you 48.5 as well. An empirical formula is really important in analytical chemistry because we often can identify compounds, like organic chemists, pharmaceutical people that are working in pharmaceuticals. They're often synthesizing new compounds all the time, and they need to figure out what's in it, and they do that by reacting the different components of it to figure out what the ratio of the elements is. If they can get to the ratio of the elements, then from there they can get to figure out what the actual compound is, what the molecular formula is. That ratio of elements is the empirical formula. So it's the molecular formula, but in a reduced form. For example, C4H8 is not reduced because the 4 and the 8 can, kind of like a fraction, like a least common denominator or something. You could reduce this to 1 carbon and 4 hydrogens, right? That's the smaller whole number ratio of carbon to hydrogen. So this is a molecular formula. The empirical formula would be CH4, right? Same thing with these other ones. This is actually sugar or sucrose, I think, glucose, I think it is. 6 to 12 to 6, well, that reduces to 1 to 2 to 1, right? And so 1 carbon, 2 hydrogens, 1 oxygen. Same thing with these other two. All right, so then molecular formulas are the non-reduced form. And now sometimes the molecular formula is a empirical formula. Sometimes they're the same thing because the ratio is 1, right? You'll see that in a few minutes here. The molecular formulas are some multiple of the empirical formula. That multiple might be 1, in which case it's the same thing, okay? So if the empirical formula is CH4, like we saw in the last one, that means that we know that the ratio of carbon to hydrogen is 1 to 4, but we don't know what the actual amounts are in the molecule, right? It could be CH4. It could also be C2H8, right? That would have the same ratio. C3H12 would also have the same ratio, right? You need the molar mass of the compound, whatever compound you're talking about, in order to figure out which of these, what is our multiple? Is it 1? Is it 2? Is it 3, right? And so let's look at an example. Let's say your empirical formula is NH3. You know that you have one nitrogen, you have a mole of nitrogen for every 3 moles of hydrogen, right? But the molar mass of the compound that you're dealing with is 34 grams per mole. What's the molecular formula? Well, we know that this empirical formula has a mass of 17, right? 14 plus 3. If our molecular formula is 34, that's twice as much. And so that means that we have twice as many elements, twice as many atoms, I should say, maybe. So our ratio, our multiple is 2. So our molecule is actually N2H6. Okay, we're just going to take that multiple times our empirical formula. All right, let's look at some steps. You want to find the mass of the empirical formula. This is kind of what we just did. Find the mass of the empirical formula. From there, you can divide the mass that you're given, the molecular mass, into the empirical formula mass in order to figure out what your multiple is. Is the molar mass twice as big as the empirical mass? Is it 3 times as big? You want to then distribute your answer through the empirical formula. That's what we just did, right? If your multiple is 2, then every molecule, every element in your empirical formula has to be doubled. And NH3 goes to N2H6, right? Another example. If a compound has a mass of 45 grams per mole and the empirical formula is CH3, so we know we have a 1 to 3 ratio in our carbon to hydrogen, what's the molecular formula? Well, the CH3 on its own, if the multiple was 1, then the molecular formula would have to be 15, right? Because the mass of 12 plus 3 is 15. But our molar mass is 45, which is 3 times greater than our empirical formula's mass, which means that the molecule itself, even though the ratio is 1 to 3, the molecule has to be C3H9 because it's 3 times greater, right? And that's where we get the molecular formula. So this is the molecular formula. This tells us how many atoms are actually in the molecule, right? The physical molecule that we're talking about. The empirical formula gives you the ratio of elements. How many carbons are there in relation to how many hydrogens there are? Okay. Let's, this one's a little bit more complex. We're giving you a percent composition, so we're kind of combining the two things that we've talked about. We've talked about percent composition, but we've also talked about empirical formulas. So if you're given a percent composition, you can actually just turn that into grams. If a sample is 40% carbon, and you say, let's say you have a 100-gram sample, that means 40 grams of it is carbon, right? So let's just convert these right into grams. Rewrite them as grams, convert them to moles, that's dimensional analysis right there, divide by their molar masses. And so we have 3.5 moles of carbon, 4.5 moles of hydrogen, a little bit less than 3.5 moles of oxygen, right? So these are our ratios of moles. We're getting close to our empirical formula. Now, to get this into a whole number, we need to divide each element's moles, so that's these here, by the smallest number of moles. So notice that we have 3.4, actually twice. That means for every carbon we have, we also have the same amount of oxygen, which means that they're in a 1-to-1 ratio. So if we divide each element's moles, that's these 3 numbers, by the smallest one, 3.4, we'll get 1, and this actually comes out to 1.5, and then this is obviously going to come out to 1. Find a whole number ratio. So we have 1 mole of carbon for every 1.5 moles of hydrogen for every 1 mole of oxygen, right? They're in a 1 to 1.5 to 1 ratio. Well, we want to deal with whole numbers, and so let's double them all. So we have 2 to 3 to 2. Okay, so our empirical formula is C2H3O2. To get the molecular formula, we would need the molar mass of our compound, which we're not given. Here's another example that you could do on your own. A good way to kind of check yourself to see if you're getting this stuff pretty well. We'll go over this one in class, and then we'll have another one, at least one more that we'll go over in class as well. We'll get a lot of practice with this. If you have any questions, if any questions kind of popped up as you were going through your notes, make sure you write those down so that we can answer them in class, because I'm sure other people will have the same questions. All right, this is Mr. Yergler signing out.